Now let us discuss the operation of the MOSFET. MOSFET operation. So let me again draw the MOSFET structure here. So let me define it's a MOSFET operation for a long channel device. Okay, let me define what do I mean by long channel device and all that. So first of all, this is the MOSFET that we were talking about, N MOSFET rather. So N plus region, and this is the P bulk or P substrate. It's often called as bulk. And this is the silicon dioxide. This region is the silicon dioxide region or oxide, and this is the metal region, and this contact is the gate, and this is the source, and this is the drain. Okay, now this is I'll take a special case where I ground the source, I ground the gate, I ground the drain, like Vg is equal to Vs is equal to Vd is equal to 0. Or the vertical electric field Vgs is equal to 0 and the lateral electric field Vds is equal to 0. Okay, this is a case where you are not getting any useful operation out of the device, but it's good to study such a condition. It is called an equilibrium condition. Okay, so in this case what happened, first of all, it's a PN junction, so there exists some kind of a depletion region. Okay, and this is N plus junction, which is heavily doped compared to the P, so you have more of the depletion region extending towards the P side rather than the N side. So let me just draw the boundary of the depletion region, and here also it is equally spaced. Okay, it's equally spaced, n plus, and there can be some asymmetry in my drawing, but it's basically symmetric on either side. Okay, that is what it is. And this particular portion from the extent of the boundary from source side N plus region and the drain side N plus region is called the channel length, L channel, or you can even call that as the gate length as far as this technology is concerned. That whatever you are considering, it's more or less equal to that of the gate length. Okay, it's the channel length, or you can say that is also equal to the gate length. Okay, and this is the depletion region boundary. Depletion region boundary. Now let me take another case where I have the N plus and P bulk, silicon dioxide, and then the gate, source, drain. Okay, now let me keep the drain grounded and source grounded and just supply some kind of a positive voltage to the gate. Okay, what happens, we know if I put positive voltage to the gate, this will acquire positive charge and it will try to attract equal amount of negative charge on the other side of the oxide, which is on the semiconductor side or P side. That is what we explained earlier, and that is what we want also. So this is the case where Vgs is greater than 0. This is the vertical electric field, and the lateral electric field Vds is equal to 0 itself. Okay, now if you keep on increasing the Vgs, there will be a point of Vgs at which the surface at the semiconductor surface close to the oxide will get inverted. What I mean by inversion is that the concentration of the minority carrier at the surface, if it is a P bulk, then the minority is electron, right? So the concentration of electron, which is the minority carrier at the surface, let me call N surf, will be equal to the concentration of hole at the bulk. So minority concentration at the surface will be equal to the majority concentration at the bulk. Such a condition is called inversion. Okay, and this inversion will happen at some value of VGS when you keep on increasing your VGS, and that value of VGS at which inversion happens is called threshold voltage, VT. Okay, it's called threshold voltage. This is very important concept in MOSFET. This VT is called the threshold voltage. Okay, so for a MOSFET to work, we said that first of all we need to have proper vertical electric field to change the conductivity at the surface. So for a MOSFET to work at all, you need to have VGS that is greater than VT. Okay, this condition is very, very important. So if VGS is less than VT, then MOSFET will not work. Okay, or this condition is called as cutoff. The MOSFET is cut off. You cannot get any current. Okay, you cannot get any useful current. This is what is the first condition, that is cutoff condition. Okay, so now what happens? So see, for what we have done, like we have said that we still kept VDS equal to 0. That means you cannot really get any current as such, because lateral electric field is anyway 0. But then we have defined that what should be the minimum value of the vertical electric field, or what should be the minimum value of the vertical voltage which will result in the vertical electric field, right? And that minimum value should be threshold voltage. And if you don't have that minimum threshold voltage, then you are going to call your MOSFET is operating in the cutoff region. Okay, now take another case. N plus oxide, and this is the metal, gate, source, drain. Okay, again the source is grounded. Usually source is the reference terminal, and see, it's just P bulk, and this bulk terminal is also another terminal. You know, for advanced courses you will have to learn that this bulk is also another terminal. MOSFET is not just a 3-terminal device, it is actually indeed a 4-terminal device. So this bulk will also be another terminal, and that also we usually ground. Okay, here also I will assume that I usually ground the bulk. It is I will, I'll explain you when I teach the fabrication that the bulk contact will also at the top, because the planar technology. Okay, so you have a situation like this, and let me say you are applying some positive voltage at the gate, and let me say VGS is greater than the threshold voltage VT, and you are applying again positive voltage at the drain now, and let's say VDS is greater than 0. Okay, and we'll say it's a small value. We'll define what is small, in some time. So if VDS is greater than 0, what happens? Now see here, in this case, let me again put the depletion region. The depletion region boundary will be like this, and because it is N type, here also depletion region will be there, and it will be symmetric all over, right? Now here VGS is VGS is greater than VT, so there will be some channel that is formed. So definitely inversion will happen, channel is formed in this portion. Okay, now depletion region will be like this if VDS is equal to 0, but VDS is now greater than 0, meaning there is some positive voltage. So if you apply positive voltage to the drain, what happens? It's a N plus, and positive voltage is applied, and this is P where it is grounded. So this is reverse bias, and in reverse bias the depletion region increases, that much we know, and more you increase the positive voltage here, the more and more depletion region boundary increases into the bulk. So now there will be an asymmetry. So depletion region increases like this, it goes on increasing. In other words, I can say with the increase in the depletion region, this inversion charge also will reduce, right? Because this inversion charge depends on the vertical electric field, like whatever this the field due to the gate voltage. Now this drain voltage is also influencing this particular charge. It is trying to reduce this charge because you are applying positive voltage here. This drain voltage will also influence the total charge that is occurred at the channel, because the depletion region due to this is increasing. Here the inversion charge will keep reducing. Okay, so you will not have a flat surface like this. You will see that it's having some kind of a slope. Okay, so let me again draw it here. So you will have a situation like this. This is n plus, and this is the inversion region or the n region, which is having a slope like this. Okay, so what does it mean? This is the gate, which is positive, and this is the drain, which is also positive, and this is grounded. This is source, this is grounded, and P bulk, this is also grounded. Okay, so what does it mean if suppose you don't have a flat surface and you have a variation like this? So it means that first of all, we know that carriers that will come from here, will start from here, and we'll have to transfer it to the drain, and it will be collected at the drain, right? So now when I have a reduction in cross section, remember here the concentration will be the same all throughout, but the concentration is number of carriers per centimeter cube, right? So per centimeter cube the number of carriers should remain the same, but then if you take the area itself, here it is becoming smaller and smaller, so the total number of carriers here will be less compared to the number of carriers here, right? So in order to have same current, the carriers that are available here should be traveling at a very large speed to give you, or very large velocity to give you more current, or to give you the same current rather, right? So this is one of the cases where you have more and more drain voltage here. You will have a situation where carriers at this portion will travel much faster to give you same current, because they are in series, they should supply same current. You can also think of another way, that you are applying a field at this side, okay, electric field due to the potential, you are applying some electric field at this side, which is in this direction, field is in this direction, so electrons will travel in the opposite direction, because field is from positive to negative. Electrons will travel in the opposite direction of the field, right? So now more and more field is available here, or as you go in this direction, the field strength will be lesser here compared to here. So more field means you will have more velocity at this side. That is what I wanted to convey. Okay, so as long as this VDS is greater than 0 and some small value, okay, we'll say what is the small value, then this situation holds true. It will still give some current which is constant current. Okay, or what I mean by constant current is, for a given value of VD, the current will remain constant or all over the channel. That is what I mean. Okay, if you increase the VD, there will be a new current. Okay, and if you increase the VG, there will be a new current. It goes on like that. Now the last case, let me draw it here. This is the gate, which is positive, source is grounded, and the drain again positive, let's say. Now say that this VDS is greater than 0, but not necessarily a small value. Okay, it's a significant value, let's say. So what happens? We know that depletion region will keep on increasing, like this. So eventually you will attain a state where your channel is almost pinched off at the end of the drain region. Before the drain boundary, it just pinched off, meaning this condition is called pinch off condition. Okay, meaning the channel is trying to be cut off, okay, at this end. Okay, so what happens? So it's not, I mean, whatever I explained here holds true also. So here also, like, you know, the number of carriers here becomes very, very small. So the carriers will travel at a very high speed at this particular, you know, portion. So there will be low speed here and very high speed here. That's how it works. Okay, and the point at which the channel gets pinched off, due to the VDS at which the channel gets pinched off, is called as VGS minus VT. Okay, if you have a VDS that is greater than VGS minus VT, then this channel get pinched off. Okay, then after, even if you increase the VD, nothing will happen, because the current will no more be dependent on VD, because the channel is pinched off already. Okay, so meaning it's not staying put, or it's not staying it's not going to react to this VD anymore, because it was till now it was reacting to this VD by increasing the slope. Initially there was no slope when you had no VD, like here, and then slowly it had a slope when you increase VD, and at some point when VDS is actually greater than VGS minus VT, the slope is in such a way that the channel is kind of pinched off at the drain end. Now you go on increasing this VD, it doesn't matter, because anyway the current is going to remain constant, because whatever comes in has to leave out, and it will leave at a higher velocity, and that's it. Current remains constant. Current will not increase anymore. That is the whole point. Okay, current will not increase anymore due to VD. And this portion, this operation is called saturation operation, saturation condition. Okay, and similarly this VDS, I said it's greater than 0, but small value, what I mean by small value is it should be less than this, less than or equal to this VGS minus VT. Okay, in this case again VGS should be greater than VT, here also VGS should be greater than VT to have any kind of useful current, and in this case it is called linear operation. Okay, so this is 1, this is 2 linear, and this is 3 saturation condition. Okay, so VGS greater than VT, the second case is the linear operation, and here it's called saturation operation. Okay.